All right, so optimization one. So as we discussed when we went over the agenda, right, the first thing we're going to focus on is the type of cycles, right? If you have two exactly similar projects, one of them is running really, really deep charges going from 90% down to 5% or to 10%, and the other is just hovering around 50% or so state of charge while kind of executing the same number of equivalent cycles per day. So both are 1 cycle a day applications. How different degradation do you get? And based on that, how much different does your overbuild capacity or your beginning of life capacity need to be? So, let's not forget the quote of a wise man who said, not all cycles are created equal. We just know someone said that. We don't know who that is, but it's true. Trust me. So let's get into the details here. So in this first section, we're basically setting the usage profile in the simulation. So we're basically using the one Maltman went over in the first section from the battery profile creator. So now that we have this, we basically just input that into the POI profile input as a CSV. And we basically have 3 exactly similar days that we're simulating. All of them looking like this. You're charging in the morning and then discharging later in the evening here. So we specify that best profile, and then we start kind of filling out the equipment models here. So here we're assuming a LFP battery, in this case, CATL's 280 amp hour cell. And the inverter model we're using here, folks might be familiar with it, is the Sunny Central Storage 4600 kVA unit. Then what we're doing is we're simply kind of varying or basically sizing the system, keeping an eye on the sizing assist tool here. So if you're following along, on your own, what you want to do is click calculate energy and power required. That way the maximum discharge and charge powers will show up in addition to the maximum energy that's discharged per day and maximum energy charged per day. So as you change these values, you put in the number of battery modules per rack, the number of battery racks per inverter, the number of inverters, and the losses you're assuming for a medium voltage transformer. And if you want to include the GSU, you can do that here as well. But as we alluded to earlier with the question around aux load, it is correct. We are assuming 0 aux load here, just kind of for simplicity. So then you start to set your kind of operational limits for your system. And one of the things I wanted to touch on that you really learn through operation is that the burden of energy management between battery racks that are placed in parallel is very sophisticated. It is not currently in the industry, it is not 100% figured out. That's why with all LFP cells out there, it is very difficult to kind of get the full range of that SOC range, unless you literally just performed a balancing cycle, which differ from one OEM to the other. So that's why really in the design process, you want to account for that, smaller depth of discharge that you have access to in your battery. So here, we're being a little bit optimistic with 93% and 3%. In reality, this would probably be more around 90%, and this would probably be 10% for most LFP batteries out there. And then here, kind of set your assumptions on battery degradation. So we're assuming we're starting off with new batteries represented by the 100% state of health here. And as we mentioned in the project performance section, we're assuming a 20-year project life. So after we run that case, this is what we get. I think the output we really wanted to focus on here was that, okay, the system we designed fully meets the requirement of the use case at year 0. So what you see in this radar chart is basically the charge and discharge at different points on the project. And what you see here in blue is the power capacity, and in orange is the energy capacity. So in other words, what percentage of the power set points and the energy set points was achieved? In case of energy, it's kind of daily throughput, basically. So if you look at all the charge throughput signal at the point of interconnect, and you want to see how many of those were achieved, you get that percentage for basically the orange here. So what this is telling me right now is that 100% of the charge set points at the point of interconnect was achieved, right? And at the inverter, the battery, and so on. And for the discharge as well, 100% of the discharge set points were achieved for both power and energy. So long story short, the system sizing is adequate. Now, where we start running into issues here is, all right, we're designing this project to be a 20-year life, but we're finding that it's actually degrading down to 273 megawatt hours, which means we're really not meeting the requirements of the use case, which is maintain at least 400 megawatt hours at the point of interconnect by year 20. So then kind of, to solve this, we need to add more capacity. So what we basically do is we start adding battery racks to the design. So before this was, I think it was 64, where is it here? Yeah, it was 64 racks per inverter. So we increased that to 91 racks per inverter. So we check kind of the output or the energy adequacy and power adequacy as well. We're still good, 100%. And what we find here is that, all right, now we have more than 400 megawatt hours at the battery terminals. Also, the state of health here is 66.8%. You will find some battery OEMs, specifically LFP battery OEMs, that allow their cells to degrade down to 65% and will give you a performance guarantee at that level. So really throughout all simulations here, we're assuming the minimum state of health or the end of life state of health is 65%.
Sharif, quick question that just came up. Where did you get the degradation model from? Any scientific publication? And how precise are the models in this regard?
Sure. So the great thing about this tool is that it allows you to input the model details and get to the equipment model. So if you click this button, it'll open up. You'll see a bunch of parameters. So there's really a lot of ways to get that. You can either have the battery OEM fill out these fields for you because really they know their system the best. You can rely on a third-party laboratory to do that. But I think from the
I can help with that. Yep, I can help with that. Okay, so it's very, very good question. Okay, the models we have in our software are validated in several laboratories, and we develop the model like using the OEM data sheets and like certified information from them to develop our models, and just to we have a generic model in our software For example, Interveni's model was developed based on the data given from them to us. So we developed our model and just validated that in their laboratory and got the results. That's why we issued a lot of battery models with this way. So go ahead, Sharif.
We've gotten kind of validation reports from Moatman. I think they did a great job with that, kind of really comparing the test results to what the model produces. So I think you can, for those validation reports, you can reach out to Moatman for that, right, Moatman?
Yeah, thank you.
All right, yeah, great question. Should we take any more? Is there a discharge?
Sure. There's another one from Wes Bolson about this section that says, do the system rule out certain battery technologies, such as Leon, when the user types in the desire for something like 100 hours of storage, 1 gigawatt, 10 megawatt system? I don't know if you might need a bit of clarification there.
No, I think I get what's being proposed. So really what will happen is if you input something that's really off in here, like you have 1,200 modules in series, and that's equating to 100 kilovolts. When you click run, you'll get a message saying that, no, your rack voltage is not matching kind of your inverter DC input voltage. And similarly, if you surpass the short circuit threshold of the inverter, you'll also get a message saying, no, the number of modules for this specific, or number of racks rather, for this specific inverter is creating too much short circuit current that, makes this really simulation inaccurate. So you have to kind of put in a reasonable design.
Yeah, and I can maybe ask a question here too. This is probably for Momin. At FlexGen, our application engineering team does a really good job of really knowing whether a certain configuration is even physically possible, because our software has to integrate with those hardware components, right? So I guess my question to Momin would be, does the model here with Storlytics actually take into account really like constructability? Which maybe Sharif just kind of talked to a little bit, but I think Momin might be best to answer that.
Yep, sure. It's taking into account that.
Yeah, and there's also, I'll mention there's a lot of custom solutions out there. I mean, the example that Wes mentioned is really out there. It has 10 megawatts, 1 gigawatt hour, so it's like 100-hour system. So yeah, I definitely haven't seen anything like that. But what you probably need to account for is that there are custom solutions out there. It's not just about what the inverter OEM is doing, but also there are a lot of battery integrators out there that put together really sophisticated fusing schemes to allow higher duration systems. Definitely not anywhere near the 100-hour duration system you have here, but more kind of like when you start getting into 6-hour to 8-hour and beyond, you start getting into like a need for more sophisticated systems, especially if your inverter has a common DC bus. So there's a lot of inverters out there that are basically multiple inverters within a single inverter. So they have multiple DC buses. So that makes life easier in a way, but they are, in most cases, more expensive on $1 per kW standpoint. So kind of pick your poison. So, all right, but really good question. Thanks, Wes, for that. Okay. So we concluded the discharge case, right? And we achieved, accomplished the mission of sizing the system. Now we want to switch basically to the shallow discharge case, right? So we're basically going to take the exact same project file that we developed for the deep discharge case, and now just input a different battery usage profile. So in this case, this is basically a frequency regulation market signal. I think it was from PJM. I may be mistaken on that, but it has exactly the same number of equivalent cycles per day as, you know, the first case. So when you look at the two, right, it's 1 cycle a day here and 1 cycle a day here. Only difference is, you know, the first case, it's deep discharges, and the second case, it's more shallow discharges, which you would expect from a frequency regulation use case or ancillary service. So we're not going to go through the exact same steps as we did on the first run, but, you know, with the design that was put together, it achieved, you know, the requirements of the use case. We found that, you know, similarly degraded down to less than the needed capacity, which, you know, we set as 400 megawatt hours at the point of interconnect. So now we're kind of going back and adding additional racks to be able to maintain that 400 megawatt hours for 20 years. So we achieved that here, and what allowed us to achieve that is 548 megawatt hours capacity. So you can see that it's quite different than the first case. I think it'll become clearer here in the comparison slide. So Adam, I'll pass it over to you here to kind of go through that comparison.
Yeah, great, thanks. And again, just to set the stage, the whole premise here is that you as the product developer and owner, you own this battery project, but you've entered into an offtake agreement, typically called a toll agreement, where you don't have control as to what the battery is told to do. The off-taking utility is making that call. And so you've entered into, the assumption here is you've entered into a 20-year fixed price toll agreement with no escalation. You've operated it well over those 20 years. You're not receiving any penalties, and assume just a $15 per kilowatt month revenue stream. For CapEx, we're assuming some fixed acquisition, development, land, and owner costs. We would say that these are not ITC eligible. Again, don't take any of this necessarily to the bank, right? This is for illustrative purposes, but we've assumed a $6.4 million number there. And then breaking down really the equipment and EPC costs, we broke them into really just 3 categories: BESS supply, inverter supply or PCS supply, and then lumped in EPC, balance of plant, EMS, and commissioning all in one. And you can see the values that we've sort of assigned to those. All in all, you'll see we're kind of approximately a little over, I think it's $300 per kilowatt hour, which you'll see in the next slide, which is pretty close to being in line with, I think, what you'll see kind of NREL publish or maybe WoodMac. If you can go back just real quick, I want to cover a few of the other assumptions though. So, some other things, because we just talked about these 2 different sizes that Sharif went through, right? One's 700 plus megawatt hours to meet the requirement, the other's 500 some. The change in size isn't just CapEx. It doesn't just have an impact on CapEx. That one's pretty obvious. It also has an impact on all of these OpEx items. So LTSA, that's typically going to be dependent upon the number of batteries you have at your site that need to be maintained. Maybe that's obvious, but obviously if you have a larger number of batteries installed kilowatt hours, then those LTSA costs are going to go up. BESS extended warranty, similarly, very directly attributable to just the battery portion that's being installed. And then other assumptions for expenses are inverter extended warranty, insurance, property tax. We don't have any costs assumed for qualified scheduling entity, because in this case, the off-taker would qualify as that and be that entity, and then also some other things as well. So tried to kind of keep it simple, but also at least complicated enough to show directionally how a change in the usage profile here impacts returns. Another, just briefly, touch on the investment tax credit. We are assuming a 30% ITC here. It's paid the month after COD. You know, that they just actually released the transferability guidance, which also impacts direct pay yesterday, I guess. And so for those that maybe follow me on LinkedIn, I did just add, there's a link to a webinar hosted by our friends at McDermott, Will, and Emery. Carl Fleming over there is fantastic. They're having a webinar tomorrow to dive into that in more detail. But the point there is they're probably, you know, you're probably not getting the full 30% there. There's probably some sort of discount, right, for transferring that credit. But again, just want to elaborate on the assumption made here. And then finally, project life. We're assuming the project ends basically the same time as the toll agreement or contract. So we're not assuming any terminal value. We're not assuming any residual value, aka kind of salvage value, or assuming that there's any cost to decommission the site. So now let's take a look at the kind of financial comparisons between the two, right?
Adam, sorry to cut you.
Yeah.
There's just a question. Just if you could explain a little bit what are EMS costs? What
is EMS cost? That's the energy management system. So that's, you know, that's actually what FlexGen provides. And so there's an upfront capital component of that, which is, you know, the servers and the software. And then there's typically an ongoing component of that for continuous software upgrades and service, which is typically part of an LTSA, or at least with FlexGen, it would be part of an LTSA. If you know, that can be different depending on who your partners are.
Thanks for the clarification.
Yeah, absolutely. There we go. Yeah, thanks, Sharif. So performance requirements, right? Sharif, we just covered all these. They're the same for each situation. And in this case, again, we're assuming no augmentation. Whatever you install in year 0 gets you through the entire 20-year life. Not the typical way to design a project, by the way, right? But here's the results, and they're kind of stunning, to be honest. So a deep discharge, you literally, as Sharif and Momin went through, would need to install 712 megawatt hours initially to meet the requirement. And we saw that the limiting factor there was really more about that 65% state of health rather than the 400 megawatt hour limitation. And another piece of that being the depth of discharge. When you do those deep cycles, you really only have access to 90%. Whereas, you know, in the shallow discharge example, so looking at the blue, you know, 547 megawatt hours, that's a pretty dramatic decrease in initial upfront oversize. So what does this mean? This means that your upfront CapEx is a difference of approximately $45 million, the 220 compared to the 173. Additionally, you see savings on the OpEx side because of that smaller, you know, less cells to maintain and service throughout that lifetime. And so what this looks like from a return perspective, and we have it shown with and without ITC. And we did that because I think we do have quite a few international folks on the call, so you may not care about our 30% ITC here in the US. But these are unlevered pre-tax IRRs, and want to point that out as well. So, you know, quite an impact of, you know, over 300 basis points in your investment returns for assuming that. So how do you think about this as an investor, right? You probably assumed the deep discharge cycle when you were running this case. You probably didn't think about shallow, and that's probably like the least risk averse approach, right? Because that's the worst case scenario. The worst case scenario is your off-taker doing the deep discharge cycles every single day, 365 for 20 years. That's what we've assumed here. And so you wouldn't build your project to the shallow discharge, but at least now you have a sense of, hey, do I want to size this maybe somewhere in the middle, take a little bit of risk that I'm going to have to augment later on down the road if I don't hit it because the worst case did happen. You know, you have to have that sort of sensitivity and information. You know, this gives you the information of what is really more of a best case scenario versus a worst case scenario from a usage standpoint. So hopefully that's helpful in shedding some light on the difference between deep discharge and shallow discharge. Sharif, what else? You know, we talked about this a lot as we were kind of pulling this webinar together. I feel like we had more back and forth on the discussion here. What other points am I missing here?
Yeah, I think one of the things we discussed that I wanted to kind of mention here to the wider group is really we're at a point where there's a lot of players in the industry that believe it's really enough to say 1 cycle per day, right? Yeah, just design us a battery that is going to be dispatched 1 cycle a day, right? As we've proven here, that's not enough, right? And I think the only way the industry will advance is kind of if developers kind of start really asking the questions, right? When you say 1 cycle a day, right? How are you going to use this battery, right? Because I'm putting a lot on the line here. I'm designing the system, right? So is it going to be a deep discharge? Can you give me a battery profile? Because I mean, at the end of the day, right, when you go out and probably all the developers on this workshop are going to be very familiar with this process. When you go out and you're purchasing the battery system, right, you're talking to Samsung CATL or any of the new integrators, the first thing they're going to ask you is, can you give me a battery usage profile? How are you going to use this battery, right? And then they're going to give you a performance guarantee. Some of them have their kind of standard, off the shelf, 1 cycle a day. In that case, they're assuming the worst case scenario. But in a lot of cases, they will say, give me a usage profile and I'll tell you exactly how much battery you need to purchase from me, right? For this project to last 10, 15, or 20 years based on what you want, right? So I think that sophistication needs to kind of expand in the industry. And I think it's going to come from developers competing and wanting to put together more cost-effective, reliable, and minimal risk projects. So
yeah, agree. And kind of to that point, just to elaborate, right? Because this is kind of assuming a toll agreement, and there's probably a ton of people on this call that, hey, I'm only doing merchant projects, and maybe I'm doing merchant projects in Texas. Well, all of this still kind of applies. You just may not have like any kind of liquidated damages if you don't actually meet this requirement, right? There maybe is no requirement, but you're trying to optimize your project to maximize revenues in that merchant market. Well, you still want to make some sort of assumption. Hey, maybe the first 3 years you're doing just ancillary services or kind of the shallow discharges. And then maybe you want to be more conservative and assume kind of from years 4 to 10, you're doing energy arbitrage, or maybe it's some kind of combo of the two. If you kind of take that next step of going to that level of sophistication, you can really optimize the size and optimize returns.
Yep. No, absolutely. And I think one point that it's interesting to me, probably most of the folks here on the, attending this workshop are probably familiar with solar and what goes into the design of solar facilities. We get really, really accurate around production estimates for energy. You calculate your levelized cost of energy, and you're probably now with the tools that are out there, you're within 2% accuracy or so. And that's solar where we're talking about PV modules that are what, 30 cents a watt, even cheaper or so, or it's probably cheaper now. So when you look at kind of now the cost of battery cells on a dollar per kWh perspective, you start to realize that, we should actually be focusing more on modeling battery systems than solar, because it's just so much more expensive. So yeah, I'll just shift here quick to some questions we received some really, really good ones. So the first one here, how do lithium ion batteries compare to redox flow batteries for O&M? This is not really covered within the workshop, but I'll just kind of relay my experience, and I'll pose that to Adam in a moment as well. But really, I think the primary impediment that's been there with flow systems has been reliability of operation and O&M. And I like that whoever asked the question, Mesmer, here, he or she are focusing on O&M, because there is a lot of maintenance required for flow systems. It's a mechanical system. There's pumps, that you have to maintain. But that's one side of it. The other side of it is the round trip efficiency. Since whenever there's a mechanical unit in the system, you start to get really much lower efficiencies. So you have to kind of account for that. And really for all battery systems, something to make sure you're aware of is efficiency is not constant, right? When we say, lithium round trip efficiency is 85%, that's a really, really general statement. It could be much, much worse if you're just keeping the battery there and not cycling it. So it's important if you're interested in a comparison between two different technologies like lithium and flow to model both and see for your specific use case which one makes sense. Because for a low round trip efficiency system, right, maybe a low cycling application will make it more attractive because you're not losing as much energy, right? So really depends on the use case. And that's what we're going to find in optimization 2 here. We're going to compare two different battery technologies and kind of expand on how we uncover the differences there. Adam, anything to add on that, or Momin?
I don't, Sharif. I can honestly just say I don't really have experience with what I would say is a kind of a real flow battery at this point. So, yep.
All right. Momin, anything on your end?
No.
All right, so we'll take the next one here. Are the profiles of renewables and customer loads provided by the utility, or Storlytics develops this information? Yeah, I'll take that one real quick. So really the profiles we're using here, they're kind of just for illustrative purposes, but the source of these profiles really depend on your entity. If you are the utility, right, and you're designing this system for to defer a substation upgrade or to provide backup power to a town that has poor reliability, so then you can pull these profiles yourself. You can get the load of the feeder you're targeting for asset upgrade deferral. But if you're kind of participating in a merchant market, or if you're participating in PJM or some other ISO, then you can look at historical data for the service you're planning to participate in. So for the shallow discharge case, we actually use the PJM signal for frequency regulation from the Reg D signal. So if you're in that environment, that's where you can get it. So really, to answer the question clearly here, it depends. Are you the utility, or are you a developer, or where exactly are you in the supply chain there? All right, I'll just take one more question, and then we'll just move on to the next optimization.
And we can leave the questions for later on.
Yep.
Sure.
All right, so RTE is seen in the AC side or DC side, and it is included the auxiliary services consumption or not. So I think we alluded to this a bit earlier, but auxiliary load here we're assuming is 0. And for lithium systems, auxiliary load is mostly HVAC. I want to say probably 99.5% of auxiliary load is lithium. It's HVAC load for cooling and heating the battery cells. The last 0.5%, that's just control load. So here for this comparison, since we're just comparing two cases, we're leaving HVAC load out of the equation right now and comparing based on everything else. But losses within the system, like copper losses, core losses within transformers, that is included here.
I can add a quick update for our next version. This is regarding our software. So in our next version, we will have enclosure models that will allow the user to simulate different auxiliary loads So you could be able just to define your enclosure model, your enclosure type, or like the adding to that the TMI profile, which allow the user to input the current temperature, ambient temperature of the site that the energy storage system will be installed in. Yep, here is the TMI profile. So using this profile and the enclosure models that will be added in our next version, and sure the battery sizes will be helpful in the giving some insights of the auxiliary load consumption based on the selected enclosure file. So just a quick update for that will be included in our next version, for more accurate results in the analysis.
Great, thanks for that addition, Moment.
Thank you.
Really helpful. All right, so let's shift to our second optimization here. I'm really excited about this one because I received a lot of questions kind of that will be clarified with this optimization.